Now we're going to look at some log rules that will allow us to simplify log expressions, or maybe sometimes unsimplify them and use them later on to solve log equations. There are going to be three rules. The first is called the product rule, then the quotient rule, and then the power rule. And if you remember, we had exponent rules that had each of these names. So these are very similar to our exponent rules. And what you have to remember is that a log is an exponent. So it won't surprise us if our exponent rules turn out to be very similar to our log rules. First up is the product rule. And the product rule just says that the log of a product is equal to the log of one factor plus the log of the other factor. So it takes one term and makes it into two terms. And whenever we go from one term to two terms, that's called expanding, because you can see it takes more terms, so it's expanded. So just for an example, let's expand log base 7 of 3x. Well, I have two factors here, so I'll be able to expand this into two terms. Log base 7 of 3 plus log base 7 of x. So see, what used to be one term becomes two terms. What used to be one term becomes two terms. Each factor gets its own log term. And here's another one. We'll do several together. Log base 5 of 25x. Well, there are two factors here, so I should be able to split this up into two log terms. Log base 5 of 25 plus log base 5 of x. Now in this case, it just so happens that log base 5 of 25 is something I can simplify even more, because I know an exponent that will change 5 into 25, and that exponent is 2. So the log base 5 of 25 becomes 2, and then I have plus log base 5 of x. Alright, here is log of 10z. Now there's no base here, so we know that the base is 10. And I have two factors, so I'll be able to split it up into two terms. It's going to be log of 10 plus log of z. Now, there's no base, so this is base 10, and I have log base 10 of 10. Well, what is the exponent that changes a 10 into a 10, or leaves a 10 as a 10? And that exponent would be 1. So this is as simple as we can make this one. And here's a third example. The natural log of 6e squared. Natural log of 6e squared. Well, there are two factors here, so I'll be able to split this up into two terms. The natural log of 6 plus the natural log of e squared. Now remember, natural log only means log base e. So what is the exponent that changes e into e squared? And that exponent would be 2. So we end up with natural log of 6 plus 2. And here is the quotient rule. The quotient rule says that if you have the log of a fraction, you still can split it up into two terms, but the term that comes from the top part of the fraction will be positive, and the term that comes from the bottom part of the fraction will be negative. So as an example, let's expand log base 6 of x over 12. So this is going to become log base 6 of x, because that comes from the top, minus log base 6 of 12, because the 12 comes from the bottom. And so that's an expanded form of this expression. And another example, log of 100 over x. So when we split it into two terms, the 100 term will be positive, and the x term, log term, will be negative. So I've got log of 100 minus, because this comes from the bottom, log of x. Now it just so happens that log of 100, since this is base 10, 10 to the second power is 100, so the log of 100 is 2, and we end up with 2 minus log of x. Now you might have noticed over here we weren't able to do any such simplifying on this example because 12 is not a power of 6. Now it's true that 6 times 2 is 12, but there's no whole number exponent that will give us 12. So 6 to the second power is not 12, it's 36. So I was unable to simplify this, as 12 is not an exponent of 6. And here's the power rule. The power rule says that if you have log of x to the m, you can write that in this form, m times the log of x. So it looks like you just take this exponent and slide it right out to the front. And why in the world would such a thing work? Well, first let's look at an example. If you have log base 5 of 7 to the third, that is log base 5 of 7 times 7 times 7. So 7 to the third can be written this way. But since this is a product, our product rule says that we can actually write it this way, as 3 separate log terms. But now they're all alike. So this plus this plus this means I have 3 of these. So you see that what used to be the exponent can be also written instead as a coefficient. And that's why the power rule works. So now let's practice expanding a few power rule problems. Here is log base 7 of x to the 5th. So if we're going to expand this, really all we can do is use the power rule on it, and we can take this exponent and move it to the coefficient position. And let's see that again. Log of 3 to the 9th. So we know that this is log base 10 because there's no base given, so we assume it's 10. And so all we can do is take this exponent and move it to the coefficient position. And again, natural log of 7 to the 4th. So remember, this is log base e of 7 to the 4th, but all I can do is take that 4 and move it to the coefficient position. Okay, now we can use all 3 properties on the same expression. Whenever we need the different properties, we can use them, any of them that we need. So we'll see a few problems here where we need several of the rules. So this first one is log base 6 of 5x to the third. Now first of all, I notice that this is a product, so let's use the product rule to write it as 2 separate terms. So I've got log base 6 of 5 plus log base 6 of x to the third, because those are our 2 factors. Okay, now I'm going to use the power rule rather, to take that 3 and put it down in front of that log term. Okay, let's see another example. Log of 100y to the third. So first of all, I notice that it's a product. I should be able to write 2 terms. This is log of 100 plus log of y to the third. Now we're in base 10, so it just so happens that 100 is a power of 10. So log base 10 of 100 will be 2. And then on this term, all I can do is take the 3 and move it to the coefficient position. Now here's a little more complicated problem. Let's expand log base 8 of the 4th root of y over 64x squared. So this time I have 2 factors in the denominator. So when I get ready to expand, I will have to subtract any terms that come from the part of the argument that's in the denominator. The first thing, we will change the fourth root of y to y to the 1/4, but we know that those mean the same thing. Now watch when I expand these bottom two factors into two different terms. It'll be minus log base 8 of 64 and minus log base 8 of x squared. And those two minus signs are because both of these pieces came from the denominator. So any terms that come from the denominator get subtracted. That's very important. Okay, now all I've done here is taken the 1/4 and moved it to the front as a coefficient. On the middle term, log base 8 of 64, it just so happens that 64 is a power of 8. So what is the power of 8 that creates 64? And that would be 2. On the third term, all we can do is take the 2 and move it to the front. Okay, let's get another example. Here is log of 10 square root of x over y to the 5th z to the 9th. So 1, 2, 3, 4. I have 4 different factors, and we know that the square root of x is really x to the 1/2. Okay, so I'm going to expand this into 4 terms. I first got log of 10 plus log of x to the 1/2, then minus log of y to the 5th because the y to the 5th came from the denominator, and minus log of z to the 9th. So these are both minus because they came from the denominator. And now let's go back and see what we can do to each term. Log of 10 would be 1 because the exponent that changes 10 into 10 is 10, well, 10 to the first is 10. Okay, so that's 1. Then all I can do here is take this exponent, shift it to the front. Same thing on this term, take that exponent, shift it to the front. And same thing here, take that exponent, shift it to the front. That's all for that one. Okay, now let's take a look at condensing. And condensing is exactly the opposite of expanding. It's just using the same rules, but instead of taking one log term and stretching it into several, we're going to be taking multiple log terms and condensing them or pushing them all back into one log term. In other words, we are reversing the expanding process. So your instructions might say something like, write as a single log term. They may not even use the word condense. It may just say write as a single logarithm, but you'll know that you are condensing or you are using the expanding rules backwards. Okay, first of all, when I look at this expression, I see coefficients in front of my terms, so we'll want to take those coefficients and put them back into their exponent position. So all I've done is taken the 4 and put it back as an exponent, and I took the 5 and put it back as an exponent. Now I see that there's a minus in front of this log term, so that must mean that when it was a single log term, this was in the denominator of the argument. So it's log base 6 of x to the 4th over x minus 2 to the 5th. Here's a second one. 1/2 natural log of x minus 2 natural log of 6 minus 3 natural log of y. So first of all, each of these coefficients has to go back to its exponent position. And then these negative log terms must mean that these things came from the denominator of the argument. So when I make it all into one log term, the x to the 1/2 goes in the top. Now I have changed it from x to the 1/2 back to square root of x, but that's kind of arbitrary. That's really just for looks. Now 6 squared is 36, and guess where it's going to belong? In the denominator. And y to the third belongs in the denominator because it comes from a minus term. And that's how you do it. But notice that it's natural log of all this stuff. All of these arguments become one argument. That's what we're condensing.